Example slide of user functions. Time guide: the slide should be finished by lap joints. A fillet welded lap joint. A spot welded lap joint. Indicates a click is required to progress to the next element. Relevant course text section page/pages if applicable. Text page ref 1, 9/10. Terms and definitions: a weld. A union between materials caused by heat and/or pressure. A joint. A configuration of members. Text page ref 1/1. Types of welds: butt welds, fillet welds, spot/seam welds, plug/slot welds, edge welds. Types of joints: butt joints, T-joints, lap joints, corner joints, closed corner, open corner. The more you take out, then the more you must put back in. Weld preparations. Remember, the purposes of a weld preparation is to allow access for the welding process, penetration and fusion through the area of the joint and its faces. The basic rule is this: the more you take out, then the more you must put back in. This has major effects on economics and distortion control, etc. The root face, root gap and angle of bevel values, the choice of single or double-sided preparations, are dictated only by the type of welding process, the position and accessibility of the joint. Weld preparations: angle of bevel, root face included, angle, root gap, root radius, root landing. Types of single butt preparation: single bevel, single V, single J, single U. Types of double butt preparation: double bevel, double V, double J, W. Welded joints: butt joints. A butt welded butt joint. A fillet welded butt joint. A compound welded butt joint. Welded joints: T-joints. A fillet welded T-joint. A butt welded T-joint. A compound welded T-joint. Welded joints: lap joints. A fillet welded lap joint. A spot welded lap joint. A compound welded lap joint. Welded joints: closed corner joints. A fillet welded closed corner joint. A butt welded closed corner joint. A compound welded closed corner joint. Welded joints: open corner joints. An inside fillet welded open corner joint. An outside fillet welded open corner joint. A double fillet welded open corner joint. A butt welded butt joint. Weld face. Actual throat thickness. Weld width 1.2.3.4. Weld toes. Design throat thickness 1, 2, A, 3, 4, B. Fusion boundary. Has. Weld root. Fusion zone. A plus B equals excess weld metal. Sizing of fillet welds: vertical leg length, weld face. Horizontal leg length. Excess weld metal. Design throat. Actual throat. Nominal and effective throat thickness. A equals nominal throat thickness. S equals effective throat thickness. A. S. Deep throat fillet welds from core and saw, etc. Concave is preferred for joints subject to fatigue loading. Fillet weld profiles. Concave. Mitre. Convex. Concave is preferred for joints subject to fatigue loading. Very poor weld toe blend angle, improved weld toe blend angle. Effect of a poor toe blend angle. 6 mm. 80 degrees. Very poor weld toe blend angle. 3 mm. 20 degrees. Improved weld toe blend angle. Effect of a poor toe blend angle. It is also possible that the height of excess weld metal is within the accepted limit of an applied standard, but the toe blend is unacceptable, as shown below. 90 degrees. 3 mm. Extremely poor toe blend, but excess weld metal is within limits. Summary of terms: weld, a union of materials. Joint, a configuration of members. Weld preparation, preparing a joint to allow access and fusion. Types of weld: butt, fillet, spot, seam plug, slot, edge. Types of joint: butt, T-lap, corner, open and closed. Types of preparation: bevels, V's, J's, U's, single and double-sided. Preparation terms: bevel/included angle, root face/gap, land/radius. Weldment terms: weld face and root, fusion zone and boundary, has. Weld toes. Weld width. Weld sizing: butts, DTT, ATT, excess weld metal. Weld sizing: fillets, DTT, ATT, excess weld metal. Leg length. Duties of a welding inspector. It is the duty of all welding inspectors to ensure that welding operations are carried out in accordance with written or agreed practices or specifications. Before, during, after all welding operations. Describe your duties to your code of practice. cswip exam. Duties of a welding inspector. Discuss the following. Before welding. Safety, legislation and safe working practices. Documentation, spec, drawings, procedures, welder approvals, certificates, mill sheets. Welding process and ancillaries, equipment, cables, regulators, ovens, quivers etc. Incoming consumables. Materials/welding consumables, size, condition, specification, storage. Marking out preparation and setup, method, angles/root face/gap values. Distortion control. Preheat prior to tack welding if applicable. Duties of a welding inspector. During welding. Preheating, method and control. In-process distortion control, balance or sequence welding. Consumable control, correct baking and storage prior to use. Welding process, related parameters i.e. volts/amps, gas flow rate. Welding run sequence and interpass cleaning. Minimum/maximum interpass temperatures. Full compliance with all elements given on the WPS. Duties of a welding inspector. After welding. Visual inspection. Non-destructive testing. Repairs. Repair procedures, NDT/excavation/welding/welder approval. PWHT. Hydrostatic testing. Submission of all inspection reports to QC departments. Responsibilities of a welding inspector. To observe. Activities and imperfections. Activities and imperfections. To record. Activities and imperfections. To compare. Attributes of an effective welding inspector. Some attributes/skills of an effective welding inspector. Honest. Literate. Respected. Dedicated. Impartial. Observant. Decisive. Analytical. Knowledgeable. Experienced. Record-keeping skills. Communication skills. Safety conscious. Inquisitive. Responsible. Diplomatic skills. A welding inspector's toolbox. A welding inspector's toolbox should contain a welding gauge, Cambridge style, or high-low gauges etc. A tape measure and scale. A wire brush. A magnifying glass. A torch and mirror. A specification, pen and report, or note paper. Any other aids to visual inspection. Specialized aids for inspection. Inspection may utilize the following specialized equipment. Borescopes, for assessing root runs in small O pipes. Flow meter, for measuring gas flow rates in MIG/MAG/TIG. Simple NDT equipment, penetrance and MPI. Complex NDT equipment, radiography or ultrasonics. Note, both simple and complex NDT methods requires the specialized skills of qualified operators/technicians. Welding imperfections can be categorized into groups. Imperfections in welded joints. Welding imperfections can be categorized into groups. 1. Cracks. 2. Gas pores and porosity. 3. Solid inclusions. 4. Lack of fusion. 5. Profile and lack of filling. 6. Mechanical or surface damage. 7. Misalignment. Cracks has hydrogen crack, initiated at the weld toe. Most cracks are initiated from stress concentrations, surface breaking porosity. Gas pores and porosity. Surface breaking porosity. Shrinkage cavity. Coarse cluster porosity. Fine cluster porosity. Blowhole greater than 1.6 mm O. Hollow root bead. Unisolated internal porosity, solid inclusions. Surface breaking solid inclusion. Internal solid inclusion causing a lack of inter-run fusion. Internal solid inclusion causing a lack of sidewall fusion. Solid inclusions caused by undercut in the previous weld run. Internal solid inclusion. Lack of fusion, lack of sidewall fusion and incompletely filled groove. Overlap, causing cold lapse. Lack of inter-run fusion. Lack of sidewall fusion. Lack of root fusion. Profile imperfections. Spatter. An incompletely filled groove. A. Lack of root fusion. Bulbous, or irregular contour. Arc strikes. Porto blend. B. Incomplete root penetration. Profile imperfections. Shrinkage grooves. Root concavity. Crater pipe. Root oxidation in stainless steel. Excess penetration, and burn through. Root run or hot pass undercut. Undercut in butt welds. Root run or hot pass undercut. Parent metal, surface undercut. Weld metal, surface undercut. Weld metal, surface undercut. Parent metal, top toe undercut. Undercut in fillet welds. Weld metal, surface undercut. Parent metal, top toe undercut. Mechanical and surface damage. Any surface damage caused by grinding, hammering/chisel marks, slag chipping hammer marks, torn cleats, hammered off attachments, arc strikes. All of the above may cause serious weakness to the weld area. Misalignment linear angular excess weld metal height. Lowest plate to highest point. 3 mm. Linear misalignment measured in angular 15. Angular misalignment measured in degrees. Mechanical testing. Which properties? 1. Hardness. 2. Toughness. Why? To establish the level of mechanical properties. Which properties? 1. Hardness. 2. Toughness. 3. Tensile strength. 4. Ductility. What are mechanical properties? Describes the actions of force and motion. Properties. Something that makes one material useful for a job. These include the properties of hardness. The ability of a material to resist indentation. Toughness. The ability of a material to absorb impact energy. Tensile strength. The ability to resist the action of a pulling force. Ductility. The ability to deform plastically under tension. Introduction to mechanical testing. We test welds to establish minimum levels of mechanical properties and soundness of the welded joint. We divide tests into quantitative and qualitative methods. 1. Quantitative tests have units. 2. Qualitative tests have no units. Introduction to mechanical testing. Types of tests include quantitative tests, hardness tests, toughness tests, tensile strength tests, qualitative tests, macro tests, bend tests, fracture tests. Testing the weldment. The test weld is usually cut into sections as follows. The location of specimens will depend upon the standard. Charpy V test, bend test, tensile test, macro/hardness test, start/stop. Hardness testing. The specimen below has been polished and is ready to be hardness tested. Equals hardness survey. Thickness. Base metal. Has. Fusion boundary. Weld metal. Further hardness surveys may be taken as the thickness of the specimen increases. Hardness testing. Generally we use a diamond or steel ball to form an indentation. We measure the width of the indentation to gauge the hardness. Hardness testing 1. Vickers diamond pyramid, always uses a diamond. 2. Brinell hardness test. Always uses a steel ball. 3. Rockwell hardness test. Uses a ball, or diamond depending on the scale. The specimen may be tested from different areas of the weld. Charpy V testing. Machined notch. 10 by 10 mm. The specimen may be tested from different areas of the weld. Graduated scale of absorbed energy in joules. Pendulum hammer. Location of specimen. Toughness testing 1, Charpy V test. 10 by 10, specimen horizontal, joules. 2, ISOD test. 10 by 10, specimen vertical, FT, pounds. 3, TOD test. Specimen used is actual design size. Detailed fracture report. Charpy V testing MN less than 1.6% increases toughness in steels. Joules absorbed. Ductile fracture. Transition zone. 47 joules. 3 specimens are normally tested at each temperature. 28 joules. Transition temperature range. Brittle fracture. -40, -30, -20, -10, 0 + 10 + 20 + 30 + 40. Testing temperature. Transverse reduced test piece. Transverse tensile test. A section of weld is cut, or machined out across the test piece and tested in tension to failure. The units are usually in N per square millimeter. Transverse reduced test piece. Radius reduced transverse tensile test. For radius reduced test specimens only. Weld. Test gripping area. Has. Direction of test. Reduced section. Plate material. Used to assess the tensile strength of the weld metal, BS 709, BSN 10002. All weld metal tensile testing. Direction of the test. Tensile test piece cut along weld specimen. Ductility elongation %. Firstly, before the tensile test 2 marks are made 50 mm apart. 50 mm. During the test, yield point and tensile strength are measured. The specimen is put together and the marks are remeasured. 75 mm. A new measurement of 75 mm will indicate elongation E 50%, Macro Inspection 8, Porto Blend 1, Excess Weld Metal Height. 7. Laminations. 6. Porosity. 2. Lack of sidewall fusion. 5. Root penetration. 3. Lack of root fusion. 4. Slag inclusion and lack of inter-run fusion. Bend tests. Bend tests are used to establish fusion in the area under test. Guide. A guided root bend test. Lack of root fusion shown here. Former. Test piece. Force. Further tests include face, side and longitudinal bend tests. For material over 12 mm thickness, side bend test may be used. Bend tests. Specimen prior to test. Specimen after test, fillet weld fracture tests. 1, 2, 3. Saw cut. Hammer blow. X. Line of fusion. 3, 1. Fracture line. Full fracture. X. 3, 2, 1, 2. Y. Any straight line indicates a lack of root fusion. Inspect both surfaces. Inclusions on fracture line. Buttnick break tests. Saw cuts. Hammer blow. A. Fracture line. B. Inspect both surfaces. C. Lack of root penetration or fusion. Inclusions on fracture line. Summary of mechanical testing. We test welds to establish minimum levels of mechanical properties and soundness of the welded joint. We divide tests into qualitative and quantitative methods. Quantitative, have units. Hardness, VPN and BHN. Toughness, joules and foot, pounds. Strength, N/2 and PSI. Ductility/elongation, E%. Qualitative, have no units. Macro tests. Bend tests. Fillet weld fracture tests. Buttnick break tests. Macro inspection. The main difference between macro and micro is that micro is the study of the microstructure at much higher magnification. The limit of macro inspection is magnification less than x10. The specimen is usually cut from a stop/start in the test piece. The cut specimen is polished to a fine finish, 400 grit. The specimen must be inspected before etching. Macro inspection. Remember, the process of inspection is to first observe, then report, then compare. Use the TWI macro sheets provided to observe and then make a report on a separate sheet of what you observe. When you have finished reporting, turn the macro sheet over and compare your observations with those given on the back of the sheet. 1 hour. A systematic method of producing a sound weld. Welding procedures. A definition of the term procedure. A systematic method of producing a name. Therefore, a welding procedure is a systematic method of producing a sound weld. What do you think about the following statements? Welding procedures. What do you think about the following statements? Do all welding procedures need to be written? Most production welding procedures are formatted on written documents or computer spreadsheets, but they need not be written and may be a product of experience. Do all welding procedures need to be approved? Most procedures are approved, but not all. An approved welding procedure is one that has been tested to ensure that the procedure as carried out produces a weld that satisfies a minimum level of quality for the mechanical, physical or chemical properties desired. If these are not required, then procedural approval is unnecessary. Welding procedures. A welding procedure is a recipe of variable parameters, which will produce the same results of certain quality and properties if carried out in the same way each time. To evaluate a provisional welding procedure, we need to check if all the parameters set will work together to produce the desired results. Welding procedures. Once the weld has been completed, it is usually visually inspected, then radiography or ultrasonic testing is usually applied. Finally, and most importantly, mechanically tested to ensure that the desired level of mechanical properties have been met. If all the desired properties have been met, then a procedure qualification record (WPQR) is completed with all the test results, and the procedure then becomes qualified. From this data, a workable document for production welding is prepared and called a Welding Procedure Specification (WPS). A cswip 3.2 Senior Welding Inspector is normally responsible for the testing and approval of welding procedures. Welding procedures examples of extensive approval include: A. Diameter of pipe, or thickness of plate. Welding position, amperage range, or number of runs. Process, on multi-process procedures only. Certain material groups. Change of consumable to one of the same classification only if the class is given in the original procedure. F. Heat input range, kilojoules/. Welder approval. Once the procedure has been approved, it is then important to test each welder, to ensure that he has the skill to reach the minimum level of quality in the weld, as laid down in the application standard. There is no need to carry out the mechanical tests of the procedure, although bend tests are often used to ensure good sidewall fusion. Normally, visual, X-ray, bends, fractures and macros are used in welder approval tests. Welder approval. When supervising a welder test, the welding inspector should 1. Check the welding process, condition of equipment and test area for suitability. 2. Check that extraction systems, goggles and all safety equipment are available. 3. Check grinders, chipping hammers, wire brush and all hand tools are available. 4. Check materials to be welded are correct and stamped correctly for the test. 5. Check welding consumables specification, diameter, and treatment with WPS. 6. Check the welder's name and stamp details are correct. 7. Check that the joint has been correctly prepared and tacked, or jigged. 8. Check that the joint and seam is in the correct position for the test. 9. Explain the nature of the test and check that the welder understands the WPS. 10. Check that the welder carries out the root run, fill and cap as per the WPS. 11. Ensure welder's identity and stop-start location are clearly marked. 12. Supervise or carry out the required tests and submit results to QC department. A cswip 3.1 Welding Inspector is normally responsible for the supervision and testing of welder approvals.